This is the last lesson of Unit 7 on vectors, and it's day 2 of the cross product. So yesterday we learned the cross product in Cartesian space, the formula that you would use for that, and we learned that when you take the cross product you get a vector that's orthogonal to both original vectors, and we looked at some different properties of them, and obviously did some sort of practice using the cross product, and again saw some of those little questions that you can have that just ask you to do things to get used to using it and thinking about what it does and that sort of thing. So day 2, we're starting out with, well, just like the dot product, the cross product has two forms. So we actually looked at the Cartesian form first, the formula in Cartesian space, and now this is the one that you could use if you're just given vectors. Okay, so we may or may not have the coordinates, but we're just given the vectors. But you're saying, wait a minute, Mr. Belair, something's crazy here, because you said yesterday that the cross product results in a vector, and that is not a vector, that is a value. That's just a number, because the magnitude of A is a number, the magnitude of B is a number, and sine of theta, the angle between them, is a number. So the product of three numbers is just a number. So this is a vector. And that's very observant of you. You're exactly right. So there's one more little detail to the cross product where we have to include this. Okay? And n is a unit vector in the direction of A cross B. So whatever that means. Generally speaking, we don't know what that unit vector would be. We don't actually have its value, but in order for this to be consistent with the fact that the result of the cross product gives us a vector, we've got to add that into the equation. Okay, it's just it's kind of strange, but it's in whatever direction the vector is supposed to be in is kind of how you think about it. And generally, for our uses for this, we don't need to know what vector it is. Okay, but it is an important part of the equation, definitely, because the cross product does have to give us a vector. So this is going to end up being a scalar. Magnitude of A times magnitude of B times sine theta will be some scalar, some constant k, times the unit vector n, and that will give us the proper outcome of the cross product. Okay. Okay. Oh, and it's a unit vector because otherwise it would change the value. So it's got to be a unit vector because the magnitude of it comes from that part, right? Okay. The right-hand rule. This is something that used to be relevant. It's not really anymore, not in what we do. I think that if you were doing some kind of applications of in a physics class where you actually need to know the direction of an electrical field that's being created by other fields or something, then this might actually matter. So I still like to talk about it just because I think it's funny, but it's not something that we're really going to use. It's related to the idea of the direction of that unit vector n. So essentially, you hold your hand the way it shows here, and you line up A and B with your vectors A and B, which would be in 3 space somehow, and the angle between your two fingers would be theta, the angle between them. And they don't have to be pointing exactly the same way as A and B. They just have to be lined up generally. And as we learned yesterday, A cross B is different from B cross A. So you have to have your index finger with the first one and your middle finger with the second one. And then your thumb will point in the direction of the resultant vector when you do the cross product. So it kind of tells you if your two vectors are drawn on a page. This is how we used to talk about it all the time. It tells you if the vector is coming out of the page upwards or going down through the page downwards, kind of thing. So again, not very helpful, but it would sort of show you the direction of the resultant vector when you take the cross product. Okay, but it's not something that we're ever actually going to use. But it's a thing. Sometimes it's useful to have heard about it. So in case it comes up and your professor next year starts talking about the right hand rule, you'll have some idea of what he's talking about, and you will not have never seen it. Okay, so let's do some examples. Again, this is with values that are given because we don't have the Cartesian coordinates of these vectors. We don't have any other definition of them, so we're just given these. Okay, so A cross B is magnitude of A times magnitude of B times sine of the angle between them, which is 70 times 68 times sine of 50. Whoops, and I already forgot the unit vector n, and we include that all the way along, and this just works out to 3,646.4 times the unit vector n, and this is like just punching into my calculator and getting that value, right? Okay, what about A dot B? Don't forget about the dot product. So that's magnitude of A times magnitude of B times cosine of the angle between them, which is 70 times 68 times cos of 50. And that one works out to about 3,059.7. And those two numbers are close, but the reason why they're close is because the angle that we were using was 50, which is close to 45, which is where sine and cos are equal to each other. So at 45, you would get the same value for a cross product and dot product. And as the angle moves further away from 45 to 0 or to 90 or more, you would notice that the discrepancy between these two results would grow, right? They're going to get further and further and further apart to the point where one of them is 0 and the other one's as big as it can kind of possibly be. So that's just all we know. Everything we know about angles of standard position, that makes sense that in this case they're close to each other, but that's not like they always are or anything like that. We talked about how the dot product is comparing things that are similar to each other, whereas a cross product is comparing the differences between the two vectors. And so, again, it wouldn't make sense for them both to be similar in most cases. So this is a new property that we didn't talk about, the parallelogram property. This is the property of the cross product. And so the magnitude of A cross B turns out is equal to the area of the parallelogram that's defined by vectors A and B when they're arranged tail to tail. So what exactly does that mean? Well, whoops, if I have two vectors, so I'm going to do vector A like this and vector B like this, okay? And let's label. Okay, then how does this define a parallelogram? Because it's not a parallelogram. Well, it's not yet, but if I do this, then it is a parallelogram, okay? And the area of this parallelogram is equal to the magnitude of the cross products, because the cross product is a vector, so it can't be equal to a vector, but the magnitude of that vector is a value, and so that's the area of that parallelogram, okay? And again, this is for us, this is a very specific question where when you're asked to find the area of a parallelogram defined by two vectors tail to tail, I'm supposed to take the cross product. So you need to know that the cross product gives us that, not the dot product, that kind of thing. But that's really about all you have to know. It might seem strange as to why this works, but if I'm going to kind of draw these again sort of differently, not necessarily the same ones. Whoops, that to be a bit more angled, actually even a bit more. There we go. Okay, and then I'm going to complete this parallelogram. So what is area? Whoops. How do you find the area of a parallelogram? Well, you multiply the length of the base times the height. That's how you find the area of a parallelogram. But if I call this vector B and I call this vector A, and here's my theta, Well, then sine of theta is opposite over hypotenuse. So that's h over hypotenuse, which is magnitude of A. So h equals magnitude of A sine theta. Okay, so we're close there. That's the height. But then the area is equal to the base, like I said, times the height, where the base is the magnitude of B. Right? So then you can see why this formula works. And I don't have the unit vector n in this case because it's area, so I just want the magnitude. So we don't need the n in this case, okay? And so that's it. That's as straightforward as it gets. Parallelogram property, take the magnitude of the cross product, and you get the area that is defined by those two, the area of the parallelogram that's defined by those two vectors. Okay, so let's try it. Given A and B, find the area of the parallelogram they form when they're put tail to tail. So here we go. I'm going to do A cross B. Okay. And again, remember how we like to write out these values off to the side. So I'm going to write out, people do it a little bit differently, but I start like that. Z, X, and Y. Okay. And so 3, 2, 6, 3, and 3, 9, -5, and 3. Okay, and so that ends up being 3 times 9 is 27 minus 3 times 2, which is 6. So I've got 27 minus 6. And then -10 minus 54. Don't be alarmed if you get some big numbers. That certainly happens sometimes. 18 plus, so minus -15. So plus 15. I think I probably mentioned this yesterday, but like being efficient at this is key. Writing this out is really useful. I see people trying to do it in their heads without writing it out. It's really hard. They tend to make mistakes. Showing one little step like this allows you to do a lot of the work in your head instead of punching it into your calculator. But it's about being efficient as well as accurate. Of course, you want to be relatively fast, but you want to be accurate. So, you got to balance between those two. So that's the vector. But what we want if we're doing the area, so then area equals the magnitude of that vector, which is the cross product, okay, which is the square root of 21 squared plus -64 squared plus 33 squared, which equals square root of 5,626. Okay. Square units. Okay, and so just don't forget that it's not going to be used. It's not applicable to any of the other things that we're going to do, even in the next unit, really. But it is a common, famous property, so it's good to do, and it's good to have to practice with our just using our formulas for the cross product. Find the area of the parallelogram formed by A and B if these are given. So we're doing the same thing, but now we're going to use the other version. A cross B equals magnitude of A times magnitude of B times sine of the angle between them times unit vector n, which is 42 times 19 times sine of 110. And that works out to 749.9. And then if I want to find the magnitude of that, and I'm just going to say area equals, then it's the magnitude of 749.9 times vector n, which is 749.9 times 1, right? Because that just has a magnitude of 1. So it ends up just being 749.9 square units. But you need to have that n up here until you actually take the magnitude of it in that step. Otherwise, it's just not exactly true. It's not exactly right. Okay. And that's that. So a couple of examples using the cross product to find some areas of parallelograms. Okay. Collinear property. Two vectors are collinear if and only if their cross product is the zero vector. If A cross B is the zero vector, then A and B are collinear, because this is an if and only if, right? And if A and B are collinear, then their cross product will be 0. Now, remember, if the dot product is 0, then they're orthogonal or perpendicular. If their cross product is 0, then they are parallel or collinear. Okay, so now we've got a test for both of these important situations that we have where two vectors are going to be either parallel or perpendicular. So this is really useful. And if you think about two vectors that are not collinear, and then we talked about this yesterday, there's only one direction and its opposite that can be orthogonal to both, right? If you only have one vector, you can have an infinite number of vectors orthogonal to it. But if you have two vectors and they're not collinear, then you only have the one direction, and it could be any magnitude or its opposite direction, that can be orthogonal to both those vectors. So if the vectors are collinear, you can't have a single vector that's orthogonal to both. You'd have infinite. So it kind of makes sense that this is what happens in this case. Okay, given A and K, prove that A cross with K times A is 0. So the first thing I'm going to do is I'm going to find KA. So it's just negative 12, 4, 16. Then we're going to do A crossed with KA. The nice thing about this is we know that these are linear, and you can look at two other vectors that are clearly a scalar multiple of each other. But since we've actually taken A and scaled it up, we know that it's scalar multiple, and so it's kind of nice to know that these are collinear, and we know how this should play out. Okay, so I'm going to do A crossed with KA. So I'm starting with the y's again. So 1, 4, negative 3, 1. And then 4, 16, negative 12, and 4. And look at this. You get 16 minus 16. And you get negative 48 plus 48. And you get negative 12 plus 12. And if you kind of think about the pattern and how we got this second set of numbers, you can kind of see why this is going to work out to 0 every time when they're a scalar multiple of each other. And so this is 0, 0, 0, which is the 0 vector. Not, whoops, I don't know where that came. Whoops, I did it twice. Oh my goodness. That's what I'm trying to do. 0 vector, because it's not 0. It's not equal to 0. It's a vector, but the 0 vector is a vector, so I can write it like that, and that's what we were trying to prove. So there we go. Okay, so that's how that would look again on a quiz for test. You're not going to be told use the cross product to prove this. You're gonna be just asked to determine whether two vectors are parallel, perpendicular, or neither. And you're going to go, how in the world am I going to do that? Well, you take their dot product, you take their cross product, and you see if either of them are 0. And if one of them is 0, then they're either parallel or they're perpendicular. And if neither are 0, then it's neither. Okay, so that's something that you have to know. You got to know which one's which, and that's what you would do to solve a question like that. Okay, last thing we're going to do is a couple of these neat little puzzle questions where you are classifying whether the outcome of each of these would be a vector, a scalar, or whether it's not possible. Okay, so this is how I tend to do these. I start picking apart each bit. So what about k times vector a? That is a scalar times a vector. Can we do that? Yes, of course. And it gives you a vector. And I'm going to cross that with vector b, so with another vector. And then I'm going to dot that with c, vector c, which is a vector. Well, vector crossed with a vector, that gives us a vector. So now I've got a vector dotted with a vector, and sure enough, I can do that, and that gives me a scalar. So therefore, the result would be a scalar in this case, because vector dot vector is a scalar. So the outcome's a scalar, but it's definitely possible. Okay. An example of when this wouldn't work is when we got down to, if we got down to the end here and it was a scalar dot vector or something like that. We can't take the dot product of a scalar and a vector. A dot product involves two vectors, right? It has to. Okay, so same thing. A cross B is a vector dotted with another vector. And then I'm crossing it with another vector. And the dot product gives me a scalar. So scalar crossed with a vector. Well, you can't do that. Cross product involves two vectors, so this is not possible. Okay, and the last one, so on top here, I've got k times a minus b. Well, what does that result in? If I'm subtracting two vectors, that gives me a vector. Okay, so now scalar times a vector, well, that's fine. That just gives me a vector. Now, what about this? What does this mean? Well, it looks fine because we're so used to this being a regular BEDMAS question, but we've never once defined any operation that's division of vectors. There isn't an operation that we know of, or that like we in this course are that we don't have that as an operation. So this is definitely not possible. And this, again, is a good example of where we get to this point and you would think some people just start making stuff up and they say, oh, well, a vector divided by a vector is going to give you a vector because you just divide the x's, divide the y's, and divide the z's or whatever, But no, that's not a thing. That's not what the way that this works, right? We can't just invent operations. So the only operations we have are scalar multiplication with vector, adding and subtracting vectors, and our other two products, dot product and cross product. We don't just make up other operations. If they haven't been defined for vectors, then they don't exist. Okay, so you got to be careful of these ones. They can sometimes fool us. Day 2 is the rest of the worksheet from yesterday. And that wraps up this unit on vectors.